Now, the first question is, why would you go for reciprocating instead of a dynamic? Or why would you go for dynamic instead of positive displacement compressors? The reason why you must use the one instead of the other is for reciprocating compressors or positive displacement compressors, they are best suited where you need a low quantity of air with high pressures. If you need a high pressure with low quantity, in other words, with low flow rates, you use reciprocating compressors. But in the event where you don't need a high pressure, but you need a high flow rates, then you use a dynamic compressors. So I said that the working principle is the same. From the previous chapter, we learned the operation of a compressor or piston inside a cylinder. So the current slide shows us it's actually the terminology that we use here. You can see in the first sketch here, the piston is a BDC. I said BDC stands for bottom dead center. And the second one, it shows TDC. TDC is top dead center. So the difference between TDC and BDC is the stroke length of the compressor or the piston. Now that VS plus VC, VS stands for swept volume. Swept volume is the length or the volume that is covered by the piston. You can see from the right-hand sketch, the piston does not move up to the top of the cylinder. It stops here. Why? Because there are valves at the top of the cylinder. If it has to go up there, it's going to collide with the valves. What happens is that small area or region or volume here, it is called the clearance volume. But now when you draw a PV diagram, we are going to replace that VC with a V3 in the PV diagram. So, okay, so this is the continuation of what we have done. Now, the VS, which is the swept volume, it is the volume of the volume of the cylinder. In other words, it's going to be pi multiplied by the diameter of the cylinder. You already know this story from the previous chapter, so I'm not going to repeat myself. Now, single stage. There are types of compressors. We have single stage, we have double stage, we have multi-stage. The multi-stage is 3 upwards. Now the question is, when do you use single stage? When do you use double stage or multi-stage? It only depends on the amount of pressure that you want. If you want high pressures, then you can go for 3 stage. But if you want moderate pressures, you can go for a single stage. You always see small compressors here. Most of them are single stage or double stage. But in big companies or plants where they need a lot of air or high pressures, they need a multi-stage. So you can have 3 stage, you can have 4 stage, depending on the amount of pressure that you require. So this is how it operates. I'm just going to repeat exactly what happened in chapter 4. You can see here there are two valves. There is an inlet valve and there's outlet valve. So what happens is that when this inlet valve opens, it is the suction side. The left-hand side is called the suction side. Oh no, sorry, it's the other way around. It's the other way around. So the suction side is on the right-hand side, and then the delivery is on the other side. So the piston is actually moving up. As it moves up, it compresses, and the valve, or it pushes this valve to open. Normally, these valves, they operate on the account of the pressure inside the cylinder. If the pressure is too high, it allows the outlet valve to open. If the pressure is too low, it creates a suction on top of the piston, so that suction will open the inlet valve. So yeah, that's the operation is more or less like a diesel or a petrol engine. Now, theoretically, we have what we call a PV diagram or a compressor without clearance. That is, in theory, we do have such compressors without clearance, but in practice, all compressors have clearance. The clearance is because we don't want the piston to collide with the valves as it moves upwards. Now, the following sketch here, the PV diagram, is a PV diagram of a compressor without clearance. So let's see what each point stands for. We have 1, 2, 3, and 4. So 1, 2, 3, and 4. Let's see what happens. At point number 1, the piston is at the bottom, it's at BDC. It's at BDC, it's at the bottom. That is point number 1. So between 1 and 2, The piston is going up now, it's compressing air from 1 to 2. How is it compressing? It can either compress isothermally, it can compress polytropically, it can compress adiabatically. But in this case, because it's PVN is equal to C, now we say that it's compressing polytropically. The question is that why would you go for polytropic compression instead of adiabatic or isothermal? One of the problems why I'm not going to ask this question in the immediate is because some of you don't even know these processes. You don't know what an isothermal process is, you don't know what a polytropic process is, and you don't know what adiabatic process is. These are the processes that we learn in chapter 2 when we do first application of first law on closed system. But for now, let's just assume that everybody knows that the compression in compressors takes place polytropically. So you can see here in chapter 1 we used to have gamma, but in this case it's called N. This N is called index of compression or expansion. But why is N? I'll explain later if it's necessary. So between 1 and 2, it is called what? The compression stroke. The piston is going up, is compressing air from P1 and T1 and V1, and then compressing up to 2. Between 1 and 2, both valves are closed. That is the most important part. The two valves are closed. Now, between 2 and 3, it is called a delivery stroke. The delivery stroke, at point number 2, the outlet valve opens. Now, it opens to allow air to leave the cylinder. Now, at number 3, the piston is at the top of the cylinder. It means that it has swept all the air that was in the cylinder out. Now, from 3 to 4, the piston now is rushing back, it's going back where it was. Its expansion process from 3 to 4 is going back. Now, at point number 4, the inlet valve opens to allow a new charge of air to enter the cylinder. So it opens from 1 to what is called the suction stroke or induction stroke. Suction and induction is the same thing. So it opens from 4, that is the inlet valve. From 4, outlet is closed from 1 to 4. So at 1 again, both valves are closed. Both valves are closed, and the piston now is compressing. It's called compression stroke up until 2. At 2, the inlet valve is closed, the outlet valve is open to allow the air that is in the cylinder to leave the cylinder. And number 3, the piston is right at the top of the cylinder. Now it is going back. It's going back. When it goes back, it creates a suction. Suction at 4, the suction opens the inlet valve, and then it allows the amount of air to come in. So for a reciprocating compressor with no clearance, we say that the volumetric efficiency of that compressor is 100%. I repeat to say that for a compressor or a reciprocating compressor without clearance, we say that the volumetric efficiency of that particular compressor is 100%. That is what is happening with the reciprocating compressors without a clearance. Now, let's move on. The power, I think the only thing that you need to know is the power. The power is sometimes called the work done by the compressor. Some people, they call it indicated power, others they just call it power. So it doesn't matter when you go through your nose or through the books. But at the end of the day, that is called the compressor power. Compressor power is the amount of power that the compressor overcome in order to deliver whatever that we are looking for. So that is the compressor power. Some people, I'm seeing that they call it work done, others they call it indicated power, others just P. That is not the case. So the work done inside this area here, 3, 2, 1, 4, 3 again, this is the work done by the compressor. This is the work done by the compressor. So normally, the work done by the compressor, we want this work done by the compressor to be as small as possible. That is what we want. That is, we want this work done to be as small as possible, because the bigger it is, the bigger your input power, and your input power is money. So you don't want to spend a lot of money in running the compressor. Therefore, you want this area inside this curve here to be as small as possible. Now let us move on to the real PV diagram of a compressor, of a reciprocating compressor with clearance. This is the real one. The real one, it means that there is a clearance. Now let's see. By the end of this session, I want you to understand what is happening at 1. I need you to understand what is happening at 2, at 3, and at 4. And again, when we solve the problems, I'm going to refer to this case here to explain things that you really need to understand. Now, at the beginning, I said that this chapter is very, very hostile to students. You know what makes this chapter hostile? It's because of the volumes. There's a lot of volumes here that you need to understand. You can see there is volume 4, is volume 1, is volume 2, volume 3, and all of that. Now, at some stage, you have V1 over V1 minus V4. We have V1 minus V3. If you can understand all these volumes here, I can assure you that this chapter is very easy. But I'll try to be as slow as I can when we are solving problems, because I want you to understand the volumes. Once you understand the volumes, you will never go wrong with this chapter. So in front of us, we have an indicator diagram or a PV diagram of a reciprocating single stage. This is single stage reciprocating compressor with a clearance. Right, let's start. At point number 1, the piston is at the bottom of the cylinder. Now, both valves are closed. Now, the piston is compressing air from 1 to 2. Now, 1 to 2, normally during compression or expansion, it must follow a certain law. The name of this path, again, I said that they can be 3. It can be polytropic, adiabatic, or isothermal. In this case here is PVN, which is polytropic. This N here is for polytropic, index of compression or expansion. So the law that compresses this is PVN is equal to constant. Compression takes place from 1 to 2. At point number 2, again, the outlet valve opens. So it is called the compression stroke. Between 2 to 3, it is called a delivery stroke. Now, at 2, the outlet valve opens. Now it is pushing all the air that is in the, not all the air, it's pushing the air that is in the cylinder up to number 3. At number 3, between 3 and 6, you can see that not all of the air is out. It only pushes the certain amount of air, and that gap here, it is that gap that is impossible for this compressor to be, for the volumetric efficiency of this compressor to be 100% because of this clearance here. So this clearance is eating into a volumetric efficiency. Remember, from the first case, there was no clearance. In this case here, there's no clearance, which makes our compressor to be 100% volumetric efficiency. I said that the volumetric efficiency is the compressor capacity, the capacity of the compressor. So the capacity of this compressor here is 100% because there's no clearance. Now, the space between 3 and 6, this is the movement of the valves. The valves open from that. So if we move this 3 to 6, it means that the piston is going to collide with the valve when it pushes the air out. So it tells us that during that movement or delivery, not all of the air is going to leave the cylinder. There's a certain amount of air that will remain in the cylinder. That is at point number 3. At 3, that air now, the valve is going to close. That air, remember, is very hot. Remember, when you compress air, the temperature increases. As it increases, the gas now is going to expand. As it expands, it pushes the piston back to where it's coming from. Now it's going back. It's moving. It's expanding. That gas between 6 and 3, it expands. It's going down to number 4. And number 4 now, between 3 and 4, the valve is closed. The valve is closed. Both valves are closed. Now at number 4, now the inlet valve opens to allow a new charge of air to enter. So between 4 and 1, the valves are open, and the piston now is moving back. At that point now, the cylinder is full of new charge of air, and then both valves close, and then the process starts again. I'm going to repeat that again so that you understand. I'm saying that at point number 1, we start with compression. Compression takes place according to the polytropic process. Normally, this N will always be given. This N will always be given. Unlike in gamma for air, we know that it's 1.4. So this N for compressors changes. It can be 1.2, can be 1.3 or 1.4, but it's always given. So compression takes place while both valves are closed. Remember, they must close. Otherwise, if you compress with one of the valves open, the air will leave. You won't create any pressure in the cylinder. So compression takes place from 1 to 2. Both valves are closed. At 2, outlet valve opens. As it opens, the piston sweeps or pushes the air from the cylinder up to number 3. Number 3, there's a small amount of air that is remaining in the cylinder that is not going to leave. At number 3, both valves close. The piston moves downwards. going downwards. Why is it moving downwards? It's because this trapped air, the one that didn't leave, is because now it's expanding. As it expands now, it pushes the piston down. Pushes the piston down to number 4. This is called expansion stroke. The first one is compression stroke and expansion stroke up to number 4. So up number 4, the inlet valve opens. It opens now, it fills the cylinder with air up to point number 1. So let's talk about the volumes. When you talk about the total volume of the cylinder is V1. Here is V1. You can see where V1 is. So V1, it is not from 4 to 1. No, V1 is from 5 years, right from the cylinder hole up to 1 is total volume of the cylinder. That is our total volume V1. The swept volume Vs, which is given by pi d squared L over 4. It is the distance from 1 to 3. The length or the distance traveled by the piston is called swept volume. So the piston is going to move from 1 to 2, from 2 to 3. So from 3 to 1, it is a swept volume. So the swept volume, in other words, is V1 minus V3. So the last volume here that we need is what we call effective swept volume or induced. See, this effective is also called induced volume. Induced volume or effective swept volume. So this VC, I don't like to use the word VC because we're using numbers. We're using V4, V1, V2, and V3. So VC is equal to V3. So the most important, the difficult part of this chapter here is for when you see this data in the question, you don't know which one is induced volume, which one is swept, which one is total. So if you can understand, you must always draw this sketch, put it down so that when you read the question, now you understand which volume is which. Otherwise, I know that the history tells me that the most important part of this compressors is understanding these volumes here. The most confusing part. I don't know why it's confusing because you can see from the sketch that V1 is the maximum, and then VC is the minimum, and then we have V1. So now when you talk about the volume, induced volume or the volume of air entering the cylinder is V1 minus V4. If you are calculating the volumetric efficiency, of a compressor is V1 over V4 divided by V1 minus V3. V1 minus V4 divided by V1 minus V3. I will again explain that when we start solving the questions. So this is the indicator diagram. Now, what we need from this case now, we need to know the compressor power or the indicator diagram, the indicated power of this compressor. Now, the area inside this sketch here is the compressor power. The area between 4, 1, 2, 3, and 4 again. This area here is called the compressor power. Again, for us to reduce, we need to have the smallest area in order to reduce the compressor power, because the higher the compressor power, the more electrical power that we are going to supply. And the more electrical power means what? The more money that we are going to pay for to operate that particular compressor. So this is where we are at the moment. So how do we calculate the power? We have to calculate this area here. Now, to calculate this area here, this is this area here. I think I forgot to explain this formula. This is the formula work done compressor power for this compressor here, compressor without clearance. So what they do, they just cut this sketch here into 2. This area 1 and area 2. They add the 2. This is they add the 2. It's the first one, the second one. The first one, the second one. They add the 2, and eventually they have n over n minus 1, P1 V1, 1 minus P2, and the final answer or the final formula is work done is n over n minus 1, P1 V1, P2 over P1 n minus 1 minus 1. So this is the work done by a reciprocating compressor without clearance. Now with clearance, now you need to have a lot of areas here in order to find this area here. Now this is how it goes. You can see here they've got area of 52126, area 5436. You add all of these areas and eventually you get your compressor power as n minus 1 P1 P1 minus V4. These formulas I will give you in the they are in the formula sheet for mid-year test. You don't have to worry about that. But I said that I won't be asking this question in the mid-year. So you can see that the V1 for the first one, V1 is from 1 to the wall to 4. There is V1 because there's no clearance. But where there's clearance, now the V1 now is no longer V1 as it is V1 minus V4. This V1 minus V4 is what? Is the induction stroke. Induction stroke, which is from 4 to 1. So for induction stroke, it's V1 minus V4 for a compressor with clearance. And then we have what we call the isothermal efficiency. I'm not too sure if I have to explain this because some of you don't know. Okay, in any case, isothermal means constant temperature. So isothermal efficiency means that it's isothermal work where T1 is equal to T2 divided by polytropic work. Polytropic work is the same as this. This is polytropic work. We call it polytropic work. You can call it indicated power. You can call it compressor power. It's up to you. But that is the ratio of isothermal work and polytropic work is called the isothermal efficiency. Now, let's have a look at this sketch here. This is very, very important. Remember what I said here? I said the compression takes place according to PVN is equal to C. Now, why are we not using isothermal compression or adiabatic compression? Let's have a look at this sketch. This sketch will explain to us or will tell us why we are using polytropic instead of isothermal. Now, remember I said that in order to have efficient compressor, you need to have not efficient, but we're always looking at the compressor that gives us a small amount of work, that requires a small amount of work in order to work. So the area between 1 and P2, this area here, we will go for the smallest areas. Now the first compression here is isothermal compression. Isothermal compression means that the temperature at 1 and the temperature at 2 is the same. Now the second one, that's when we compress isothermally. The second one, the middle one, is the polytropic. Between 1 and 2, the middle one is the polytropic. But we can see that the area now increases from isothermal to polytropic. And the last one again is isentropic or adiabatic. Adiabatic between 1 and 1, here is the area. So which curve gives us the smallest area? From this case, you can easily see that the isothermal curve gives us the smallest area. But the problem with isothermal is that on paper, yes, you can compress air isothermally in such a way that temperature before compression is the same as the temperature after compression. But practically, it is practically impossible. So because it is practically impossible to compress isothermally, we use the closest one. The closest one is the polytropic compression, which is PVN is equal to C. Adiabatic is PV gamma is equal to C. So that is the reason why we compress gas according to PVN. We can compress it isothermally, but practically it's impossible because the temperature, every time we compress air, the temperature increases. So it's impossible that temperature at 1 can be equal to temperature at 2. Virtually impossible. So hence, we go to the closest one. The closest one that can give us the smallest area is the polytropic work. Okay, so here are examples and the mechanical efficiency. The mechanical efficiency is going to be what? Polytropic compressor work divided by work input. Work input is coming from the shaft. It's the indicated power divided by shaft power. That gives us a mechanical efficiency. We will explain this mechanical efficiency when we start solving problems. And if I'm not mistaken, I'm sure I had some noise on the chart. Let me go back and check if there are any questions. Okay, for a chart with the clearance, sometimes it's given, sometimes you have to find it, but that's one of the formulas. VC is equal to total volume. Yeah, that's correct. Dante, Ethan, yeah, that's correct. Clearance volume is V1 minus V3, yes. That's clearly seen on the diagram, okay. Yeah, just stating if it was lost in the translation, my bad, okay. Yeah, I just got concerned or connected. Does anyone else have audio? VC is equal to, that's correct. Yes, Dante, we can watch. Okay, guys, before we move on now to solving problems, because like I said that I don't want to go through to two-stage and multi-stage because of the problems that we have with chapter 1. Let me just go back. So this is where we are now, mechanical efficiency, and then we have examples of volumetric efficiency. I said that it's a capacity, compressor capacity. So when you compare the compressors, and then we make use of a volumetric efficiency, which is a V1 minus V4 divided by Vs. Vs, I said, is a solid volume, V1 minus V3. And then from there now we have multi-stage. Multi-stage, we're not going to be doing that, but multi-stage is if we have more than one compressor or one cylinder. In this case here, you can see that this is your first stage. This is called the low pressure, and then you've got this high pressure, the second stage. So you can see from here that's intercooler. What is an intercooler, or what does it do? When you compress the air, air enters the first stage. It gets compressed. When it gets compressed, now it leaves at P2 and T2. Pressure has increased, temperature has increased, but now in order to have, reduce the temperature, we use an intercooler. Sometimes they use air, sometimes they use water. But the small compressor that we always use, they're air cooled. Others they use the one that we have in a thermo lab, they are water cooled. So when we do lab 2, we do compressors. Then we will also introduce to intercooler. Intercooler is between the cylinders, to make sure that the temperature at that point is the same as temperature at the beginning. So you will say that it's isothermal, but in practice, it is impossible that the T2 can be equal to T1. It's only if we have a perfect intercooling. In other words, T2, the temperature at that point is equal to the temperature at the inlet. Now the question is, what happens if we allow the gas or air from number 2 to go into the second stage without being intercooled? It's simple. Now, when you allow the air without intercooled, once it enters there, it expands. When it expands, what happens to the pressure? The pressure drops. All the first thing that we don't want to have in compressors is a drop in the pressure. So to avoid that, we make sure that we stop it from expanding. How do we stop it from expanding? We intercool. We push it through water or through air so that the temperature does not change. Now, that is the main reason why we have to intercool, to make sure that the temperature remains constant so that it doesn't expand. Once it expands, the volume increases, but the pressure drops. Remember, the volume, the pressure and volumes are really not friends. If one goes up, the other one goes down. So now the very reason or the objective of the compressor is to increase the pressure. And therefore, we cannot allow the pressure to drop. Therefore, we have to intercool to make sure that the specific volume of gas is as small as possible. Once we allow it to increase, it means that the pressure drops and the volume increases. That's why we have this intercooler. And then this is the PV diagram of a double stage without clearance. Double stage, this is stage 1, low pressure, and this is stage 2, high pressure. So theoretically, we would want to have the compression to take place from 1 to 2 and 9. This is isothermal compression. Like I said, that isothermal compression in practice is impossible. We cannot have isothermal. Therefore, we have polytropic from 1 to 4, and then between 2 and 4 and 2, this is called what we call intercooling. You bring water here now to reduce the specific volume. You can see that from 1 to 4, the volume V4 is bigger than V2. So to bring it, to make it smaller, you bring water. So this is intercooler between 2 and 4. Now from here again, you compress it again polytropically. PVN is equal to C. This is the other one. Now, if we decide to compress it adiabatically, you can see from 4 to 5, this is the area where we are going to use excess energy to compress. So to avoid that, this shaded area is the same, the amount of work that we save by compressing polytropically.